Hello guys. I'm recording this video to help you on lab number 5. So yeah, so in this lab you are gonna learn seven segment. Okay, let me see here. Yeah, you are gonna learn a segment. You will know how can you use it and the structure of the seven segment. So let me give you some help here. First of all, I explained before an LED, right? And in previous labs, you already have used LED. I told you an LED is, this is the symbol for an LED. I told you as a device, it should look like something like that, and it has two terminals like this one here. So here, one of them, I call it anode, which is this one. So this is anode, and the other one is called cathode. Okay, and the way you have to use it is, if you want to turn it on, so the voltage here at the anode has to be greater than the voltage at the cathode. Okay. Also, what we did before, you have to connect the resistors here. Okay, and this resistor is called current limiting resistor. It is used to limit the current. If you forget to connect the resistor, you are going to burn it out. You got what I'm saying? Because it's too much voltage for it's going to be too much voltage and too much current for the device. So for example, I can do something like that. I can put here, for example, 5 volt or whatever. In this case, current is going to flow this way and you can turn it on. Is that okay? However, if I put here 0 voltage instead, if I put here 0 voltage instead of 5 volt, so that means the voltage here at the anode is not greater than the cathode. Cathode is 0, okay? So in this case, this one should be off. All what I need from you in this course is just to know, number one, what is this device, what is doing, what this device is doing. Also, you need to know how can you use it. That's it. When you take courses in electronics and other courses, you will know the details of these devices. Okay, so why now I'm talking about LED? Because we have what we call 7 segment. Okay, this one is called 7 segment. I'm quite sure you are familiar with, you have seen something like that before. Okay, so actually this 7 segment, it is used to make numbers. For example, if I want to make number 2, as you see here, it has 7 segments. So one segment, let me explain it slowly first. So as you see here, this one has 7 segments. So this segment, we call it segment A, B, and C, D, E, F, G. Is that okay? You can, every segment is an one LED, separate LED. So you can turn on and off each segment individually. You got, this is the main point. This is the main point. Okay. So actually it looks like here, as you see here, this A alone is one LED, as you see here. B is one LED. So every segment here is just one LED. And then the cathode, all of them are connected together. Okay, and this type of 7 segment, we call it common cathode. Common cathode because all the cathode of all segments or all LEDs are connected together. Is that okay? So a very important thing here is this 7 segment does not have these resistors. You have to connect this resistor. Please don't forget, because if you don't connect these resistors, simply you are gonna burn some segment off. So you have to be careful about. So it doesn't come with, you need with a resistor. You have to connect this resistor externally. Anyway, so the main idea here, this is common cathode. If I connect it to ground, for example, and then I put here 0 volt. So this LED is off, right? Because I have just said the anode has to be greater than the cathode. If I put here 5 volt, so this one is on. So by this way, I can control which segment here are on and off. Okay, and then based on that, I can display different numbers. For example, if I want to display number 0, so I have to turn A, B, C, D, E, and F on. Is that okay? To make 0. If I want to make number, for example, here number 9, so this one on, and this one on, and the other ones here are off. This is the main idea. So by turning some LEDs on or some segment on and the other segments off, I can make different numbers. This is the main idea. Okay. So here I give you, again, as I said before, don't forget, you have the hyperlinks here. So if you want to read more, if you want to understand more, also you have the data sheet. So you can get the data sheet of this 7 segment. Also, you can, all what you have to do, just click on the hyperlinks here if you want to know more information. So this is how it is. This is very simple. So for example, before I move forward, for example, here is, as for example, I want to display number 3. So here, this one on. Okay, so to display number 3. So it has to be A, B, C, D, and G. So for A, I am gonna put 5 volt. Okay, B, I'm gonna put 5 volt to turn it on, right? A, B, same thing for C and for D. Okay, but and G. Okay, now I want to turn off F and E. So here for F, I'm going to put here 0 volt and 0 volt. That's it. If I do this way, you can see number 3. Okay, so every number, for every number, I have to turn some of them on, some of them to display this number. Is that okay? So the second thing here I want to talk about, and this is also very important thing, we call it a driver. So you will understand what I'm saying here better in electronics, but at least I'm going to make very basic definition what I mean by driver. Okay, so so here you have this chip, so you can read, you can download the data sheet and understand it. Okay, so what this driver is doing, actually, this driver should do 2 things, by the way. Okay, the way you have to do it, this is a chip, this is driver here, so this is the driver. Okay, and then the output of this driver, you have to connect it to the 7 segment, but don't forget to put resistors here. This is the way it has to be. Okay, so what this driver is doing, okay, why I need to connect it this way, I'm going to tell you how. So this driver actually is going to do 2 things. So this driver, it has 4 inputs, as we see here. This input are BCD, binary numbers. So this input can have actually binary numbers from 0000, okay, which correspond to number 0, until 1001, which is corresponding to number 9. I should not anything after 9, like 10. You know, this as I said in lectures, this is 4 bits. So 4 bits can go up to 15. But for sure, this one you can only input numbers binary from 0 until 9. Okay, and then what this one is gonna do is gonna actually, it has inside it has a decoder. Okay, I'm going to teach later in this course how can you design this decoder. So in this case, if the input, so here let me clear this one here. Okay, so what happens is that I'll give you one simple example to understand it, the basic idea here. Okay, so here, if you input here 0000, okay, so there is a decoder, okay, or there is a logic circuit inside this one. This logic is this is input of the logic circuit. The output of this logic circuit is gonna turn some LEDs here. It's gonna put here 5 volt or 1 and 0 volt or 0 logic 0 for some inputs here, so that you can see number 0. Okay, so here, if I want to make like a truth table for this one, for sure, forget the details. So I'm going to teach it later in details. So this is the input. So the output here should be A and B, C, D, E, F, G. Is that okay? The 7 segment I have. So in case if I want to display, let me clear here something quickly. Okay. So if I want to display, okay, If I want to, so here, if the input is 0, 0, there is a logic circuit. This is like a truth table. This is, you are going to design it later, so forget the details. If you input this one, so the output here of the logic circuit here is actually is going to turn this one on to make it like 0. So it's going to put 1. The output here has to be 1 everywhere except G. So it has to be 0 and 1, 1, 1, 1, 1. Is that okay? This is how it is designed. What if the input, for example, is number 9 or any other number between 0 and 9? For example, I'm taking 9 as an example. In case of 9, okay, so actually the output of this circuit has to be, we need to turn here. You don't need to do all of that. I'm just explaining how it works. Okay. So here it's going to be this way. Okay. To display number 9. Okay. So this chip is going to convert your number, BCD number, into a code, so that when you input this code to the 7 segment, you can see this number. You got what I'm saying? So for example, in case of 9, so I'm going to put 1 everywhere except E. So E is going to be 0, and again the circuit will put 1 everywhere. Don't worry, in this course we are going to design this circuit. Okay. So this is one of the things this chip is doing. There is another thing here. This usually this chip is doing is, but this is the main functionality of this chip. But also this kind of chips, what they do, sometimes I hear I'm gonna connect this one to my USB, for example. But USB, my computer USB does not have enough current to turn this one on. Okay, so in this case, we put here what we call a driver. So this driver, okay, so this is connected to USB. So it's gonna take very little current. It's gonna take very little current from USB, and then it can provide too much current here. Okay, so this also we call it a driver. So this chip will do that. So where is this much current, where it will come from? Yeah, this one you have to connect it to VCC and the ground. Okay, but anyway, this is not the main functionality anyway, but some of these chips do that. But this is not the main functionality. The main functionality, as I told you, it has to convert the BCD code into 7 segment code. BCD code to 7 segment code. Okay. One of the things is here. So this chip, it has 7 outputs. 7 outputs here. You have to connect them here, but you need to connect the resistors. Okay. Also, it has 4 inputs for the BCD numbers. Okay, and we call them D0 to D4, as you see here. I think where I mention it. Anyway, I think it's coming somewhere. Okay. Also, on top of that, it has also some inputs here that have some special functionality. Let's see this input. So one of the input here is test input. This one. So this one means what this one is doing. Is actually this one is used if you want to test the 7 segment. If I want to see if the 7 segment is working or not. So in this case, if I put 0 here in this input, okay. So actually this will turn all the LEDs on. Okay. By this way, I can check if I can make sure if all the segments are working or not. Okay. We have another one here. We call it blanking input. So this is chip. It has one input, okay, which is this one. If you put 0 here, you actually turn all of them. This is just used for, this one is used just for testing. The other one, we call it blanking. So if you put here 0, you blank it. Blank means you turn all of them off. You got what I'm saying? So if you just put here 0, you can blank it. So you can see this input as like enable or disable. Okay. So if I put here 0, I actually disable, so you don't see anything here. Okay. If I put, regardless of what values you put in this BCD input, I told you we have BCD inputs, and on top of that we have also these 3 inputs. So regardless whatever you have in BCD, if you just put here 0, okay, so actually you are gonna disable it. It's gonna be blank. You're not gonna see anything. Okay, that is why for normal operation you have to put here 5 volt, or you put 1 here, or 5 volt. Same thing here, you have to put here 5 volt or 1. Okay, the other one here is called latch enable. Okay, what latch enable means? I'm going to tell you what it means. Okay, you have here the three BCD, as I told you. If you have a number here like number 1 or number 3 or whatever, we have some number here. Okay, so actually here this one, if you put this one 0, okay, that means the input here is not going to be converted into 7-segment code until you make it 1. You got what I'm saying? So that's what we call, you allow the decoder to store the last data present on the 4 input. Okay, so that means if you yeah, so here so in this lab you have to put 0 here. You have to enable this latch. Okay, so if you put here 0, you enable the latch, so that the decoder, I told you this decoder is converting. This is one of the main parts here, is a decoder that convert the input here into 7-segment code. Okay, so if you put here 0, so actually whatever you put here is going to convert it. If you put 1, so whatever you put here is not going to be you can't see it in the output. Okay, but anyway, for this lab you can just put 0 all the time. Sorry, for this one, yeah, for this one you need to put 0 to enable it. Okay, so that you allow the decoder to store the last data. You need to check. I'm not quite sure, but I'm not sure if you need. You can ask the TEs about this one. If you put, because it's not clear to me here, if it allows the decoder to store the last data represent on the 4. So it's not the current. Yeah. So this one here allow to store the last value. For example, if I put here value 0, 0, 0, 0. Okay. And then you latch it. You put here 0. Okay. So once you put it 0 here, these values are gonna go to the decoder, and then you can see it at the output. Okay. And then if you put here 1, I'm not sure if it works this way or the opposite, but you can check anyway. You can check the data sheet anyway. But one of them, whatever you put here, you are going to be shown on the output. The other number, if you put it here, okay, it's not going to be converted. It's not going to be shown here. Okay. Look here. I think it's clear now. Look here. Oops. Okay, let's see. Because things like this are different from one chip to another. So that's why you may, if you in the future, if you bring a different chip, you need to read the data sheet to see how it is made. So because it may be different, but I think it's very clear here. When the latch enable input is asserted, okay, so the 7-segment output are determined based on the bits for PCD inputs. Okay, so when yeah, so for one input, you are going to take the current value of PCD. For the latch here allows the decoder to store the last one. Okay, not the current value, no, the last value. Okay, so here I think 0, so that's why I think you have to make it 1. But anyway, you need to ask it here, or you can try it. Okay, so here, because it's not clear here which one, but you can even read you can figure it out from the data sheet. The latches here captures and store the data present on the 4 input. Enable is uncertain. Okay, so, sorry, unasserted. At the time the LED prime input transition from low to high. Yeah, so I think that's what it's correct. So now I think it's clear now. If you put here from low to high, when it goes from when it becomes low, sorry, it's the opposite. Yeah, it's from low to high when it is low, and then becomes high when it is 1 here. So actually, yeah, that's what. So you have to put here 1 if you wanna. Yeah, I think it's very clear here from the text, but you also, it's very recommended in this course to read the data sheet anyway, because in the future you may use a different chip, and in this case you need to read the data sheet anyway. Okay, so I think from the text here what's written, if you put here 1, so whatever you have here, you will see it the output here. But if you put 0, here in this one, so this one is gonna store only the last value before you put 0. Okay. Anyway, so Here, let's look at the Prelab. In the first part here in the Prelab, I give you this. I think in the lecture I have to explain. This is one way to represent the function. Using this one, you can make a truth table. Okay. So here I'm asking you to use algebra manipulation to reduce this one. Okay. You have to sum of product. Also, I told you after you summarize this one, you need to create a truth table to prove, and you can prove the simplified version is true. Is okay. How can you prove it is true or not? Okay. Well, what you have to do is, for example, I simplified it and I found some relation. Okay, I'm gonna put something random. Okay, for example, B, C, or A. For example, okay. By the way, this is not correct, but something random. So this is a simplified version. For example, okay. So all what you have to do in the truth table. Try to see at in row 0, row 3, row 4, row 7. Okay, if you can find once at these rows and zeros in the other rows, so you are correct. Okay, so that means this function is giving the same thing like the original one here. Okay, and then here I ask you to implement it. I asked you to implement using digital tool. Okay, then I give you here, this time it's more number of variables. So here I give you 4 variables. I give you this one here. Remember, this is by, if you go to the lecture, so these are the location of zeros. The other rows, the rows that are not here, should have ones. Okay, and then here I'm asking to use Boolean algebra to simplify this one. Okay, by the way, try to do your best, and you have simplify it, and you have to put it in product of sum. Yeah, using algebra to manipulation to and draw. Yeah, you have to simplify it using Boolean algebra, and you have to put it in product of sum. So how can you do that? Number one, you have to make the truth table. So here you have A, B, C, D, and then you have F. This is F here. So F here in F, you have to put zeros in this location. In other locations, you have to put ones. Okay. Then once you have F, I can make F prime. So F prime here, every bit here, you just flip it. Okay. And then after that, you have to calculate sum of product, okay, of F prime and simplify it. So calculate sum of product of F prime and simplify it. Okay. Then after you simplify it, why F prime? What's not F? I'm going to tell you why. Okay. Because once you have F prime in sum of product format, you can, using De Morgan, you can convert it to product of sum. You got what I'm saying? Product of sum. I'm going to say it again. Number one, create a truth table. Okay, for this one, you already have the information here. Okay, for F, and then you calculate F prime, and then calculate sum of product for F prime. Okay, and after that, simplify this one. Okay, after you simplify it, you will get it in the format of sum of product, and then calculate. Once you have it in sum of product, when you calculate the De Morgan to get F, is going to be product of sum. For example, let me give you an example here. For example, if I calculate F prime is equal something like that, anything, okay, A, B, C, or D prime, B, whatever, A, for example, if it has something like that. So when you calculate F, is going to equal, okay, I'm going to calculate De Morgan for this one. When you calculate De Morgan, this one, you are going to get A prime or B prime or C prime and D or B prime or A prime. Okay. So as I said in the lecture, this or is converted to and. Also, as I said in the lecture here, when you calculate De Morgan for this one, everyone is going to be complement. You have to complement everyone, and any and here you have to make it or. Okay. So this is how can you do it. But be careful here. And this is something you need to learn, and this is also what I said in the lecture. This is because it is 4 variables, okay? And as I said in the lecture, Boolean algebra manipulation is not the best way to do simplification, and you may not be able to get the most simplified function. Okay, that's why usually we use maps, but still you need to learn Boolean algebra. So just do your best to simplify it. But if you don't get the most simplified one, I'm totally fine with that. If you don't get the most simplified one, but just to do your best, okay, to simplify it, okay, because and you will see when after I teach the key maps for variable, you will see how it is much easier than doing it using Boolean algebra. Okay, one of the things here I want to tell you, maybe some student may not be able to simplify it enough, for example, and because you need to implement the simplified function. Maybe you don't have enough chips, for example. If you are not able to simplify it enough, if you simplify it enough, you should have enough chips. But if you don't simplify it enough, you may not be able to have enough chips. So in this case, I'm totally fine if you just use the simulator for this one. Okay. Again, the main thing here, maybe I recommend after I teach the key maps, try to do the same thing using key maps, okay, to see if what you got is the most simplified or not, and also to understand. Usually, we don't use Boolean algebra for simplification, because maps is much easier as I said before. But you need to learn both. That's how it is. Okay. Yeah, so here I'm telling you, this is the PCD input, D1 to D4, and then we have other inputs here, okay? Don't forget to connect resistors, okay? Here I'm asking you to connect, here on your board, to connect the DIB switches as we did before. You remember when we did the DIB switches, like if I have a switch like this case here, so don't forget to connect resistors. Okay, for example, 5 volts this way. If the switch is open, I'm going to get 5 volt. If the switch is closed, I'm going to get 0 volt. So using the switch, I can input logic 0 or logic 1. This is the main idea. So here in this part, I'm asking you, let me see what I ask you to do here. On your board, connect the DBI switch to each input of the BCD here, driver chip. And I'm sure you need to read the data sheet, but I'm sure this chip should have a ground. You have to connect it to ground. I'm sure it has VCC, so you have to connect to 5 volt. It may not have VCC. I think it has. Anyway, so you need to read the data sheet and see if I think it has 5 volt. You can. I think yes. Yeah, it should have ground. Don't forget to connect these ones. Okay, it must have 5 volt and ground. Okay. So here I'm asking you to connect here the switches to the driver, okay, and then here using GIB switches, and then after that you need to connect the 7 signal. Don't forget to put resistors here, and then using the switches here. Remember, we have 4 inputs here. Using the switches, you can play. You can see if I put 0, 0, 0, 0, I should see here number 0. Okay, if I put here number 8, I should see 8. Number 3, I should see number 3. Here you put it in binary, but you see here the number in decimal. Okay. Okay, let me see if I did something else here. Yeah. Don't forget to connect the resistor, please. Okay. Okay, so in the first part here in this lab, here I'm asking you to implement the minimize. I give you 2 functions before. You should have simplified this one and the other one. It's a second. So for this one, you need to implement it, okay? And you need to check. So here, this one, there should be here the circuit. This circuit should have ABC, and then it has one at the output here, okay? So I want you to test using a pattern generator. You remember what I said about what you did in pattern generator in last lab. So here in pattern generator, you have A, B, C, D. Sorry, ABC, as you see here. So here you generate timing, something like that, timing diagram this way. Okay, so it should be here 0. Here, for example, it should be 0, 1, 0, 1, 0, 1, 0, 1. Okay. No, sorry, I think this should be at C anyway. It's not a big deal, but it can be ABC. So I think, and when I say ABC here, C is the least significant one. So C, B, and A. Okay. And then this one should be 2 zeros, 2 ones, 2 zeros, 2 ones, and then 4 zeros, 4 ones. Okay. So these are all possible cases. And then you can choose the output as well. So you need to, so here, using a pattern generator, you can input here all possible cases, and then using logic analyzer, similar to what you did last time, you can see the input and you can see the output, and you need to get a graph, something like that. Okay, to see the input output, and by this way, okay, and by this way you can know if the function is correct or not. If your circuit is correct or not. So if you look at the truth table, if you look at the output here and you find it similar to the truth table, so your implementation is correct. Okay. Let me see. You already built your whatever, then you have to, yeah, that's what I'm saying. You have to connect it alongside here. So you are going to do two different separate things. Don't be confused here. So this is your logic circuit. Okay, for this one, this is your logic circuit. You have here ABC, and also you have here the output of the function F. Okay, for example, also you are going to put here the driver, and you are going to put here the 7 segment. You are going to put the 7 segment here. You put resistor as I told you, and then you take the input, you put it here. Okay, so they are like separate. They are separate. So the same input here are going to come to here. Okay. And this is the interesting part. And then, because I'm going to select the frequency of 1 hertz, 1 hertz is a small frequency. Okay. By this way, it has to be low frequency. By this way, what you are going to see here, okay, is actually ABC. So ABC is actually, you are going to see 0, 1, 2, 3 until 7. Okay. Then after 7, you go to 0 again. So by this way, what you have to see here on the 7 segment is like a counting. You see 0 for some time, and then number 1, number 2, number 3 until number 7, and then after 7 you get 0 again. Okay. Anyway, this is the first part. In the second part here, I'm asking you to implement this one. I'm flexible regarding, yeah. Here I told you implement and test it using the chips you have. Okay. I'm a little bit flexible about this one because I understand to minimize this one using algebra. It may not be, if you can, again, I'm not looking for the most simplified, but if you can get this, will be great, because this one was a problem in algebra manipulation. It's not easy to get the most simplified. Anyway, so if you can simplify it and you can implement it, that's great. If you can, so this one should be enough until the T is as that I said, this one should be enough. If you simplify this, simplify this one, and then you don't have enough chips, for example, because you didn't do enough simplification. Okay, so the simulation should be enough for this one. In the last part here, part 3. In part 3, I want to measure the delay between. Again, I have here a function ABC. Okay, and this is here the output here F. Okay, so if after you put some value here, how much time is going to take until you see it at the output? This is the delay we had before. Okay, so actually maybe, yeah, maybe I revealed a secret here. Okay, so actually after you do the simplification of this function, you are not going to have A. So your simplification should have only B and C. So as you see here, only B and C. Okay, so what you have to do here, you have B and C. Okay, so what you have to do, I can put some value here in B, like for example, I can put here 5 volt, for example, and then now at C, I change C, for example, from 0 to 5 or 5 to 0. 5 to 0, and then I measure. So here, let me. Because I want to measure the delay. So by doing this change, for example, when this one is 5, again, you have to go to the truth table. For example, the simplified one, for the simplified one. For example, if B is 1, okay, and C is 0, the output, for example, if it is 1 and 1, just an example, F equal to 1. Is that okay? However, if I make this one 0, F has to go to 0, okay? So in this case, what I can do is, in order to measure the delay, I can put here at B, I put 1, at C, I put 1, F is 1, F is 1, okay? And then I change this one from 1 to 0, and then I look the output here. The output also has to change from high to low, and then I'm gonna see what is the delay here, how much delay here. You got what I'm saying? So you have to fix it 1, okay? And then you have to select a certain value for the second one here, so that the output, one time it changes from high to low, to measure the delay, because as we explained before, you have two types of delay. You have high to low delay and low to high delay, to measure the delay between the output and the input. Is that okay? I think that's it. So the last part here, I'm asking you, in your own words, describe the functionality of this input here. Okay. Again, you can go to the data sheet to better understand. I already explained it here. Second part here, I'm asking you, formulate a design scenario thing. Here I give you some question to, I just want you to think about them. So you can think here about a design scenario where each input here and this 3 input is required to obtain a specific observable response on the 7-segment display. So so you need to think about this one. How can we use these inputs somehow? Okay. For example, I can tell you something quickly. For example, this one here, this one you can make it blank. Okay, so there is no reading. For example, if you are doing some measurement and the measurement is going to take some time, so I can make it blank, and then I do the measurement, and then when I am done, I'm gonna turn it on. For example, you can think in other scenarios here as well. Okay. Here I'm asking you, are the implementation of F and G correct? Very simple. All what you have to do is that after you implement the circuits, okay, you need to you need to check the results you got with the truth table. If you get the same truth table, you are okay. In the last part here, I'm asking what is the maximum propagation delay. So here you need to measure the propagation delay here for different cases. Okay, low to high, high to low. Also, you need to low to high and high to low. Also, you have to measure it when I told you we are gonna fix B and then we measure from C. You can also do the opposite. So here I can put, for example, here for B and C. For C, I put 1, and then I measure the delay from B to F. You get what I'm saying? So you can measure several delays. Then at the end here, I'm asking you why this delay is, why such delay, propagation delays are important, and why is gonna some impact on the design consideration. As I told you before, these delays can determine the maximum operating frequency, the maximum frequency for the input. You can't, very simple, you can't just make the input very quickly. The input, I can't input very fast frequency in the input, and the output, it did not show the result yet. Okay, in this case, it's not going to work. You understand what I'm saying? So that's why I have a restriction on the operating frequency. I have to wait. I have to make sure when I give certain input, I should not change this input to another input. And okay, so I have to keep them for a certain time. For example, as I told you, for example, if this is C and this is B and this is E, for example, okay. Okay, so here, what is the time here? What is the time here? What is the time here? Okay, this time should control the frequency of the input, okay? And also this time has to be related somehow, or propagation delay is gonna put a restriction on this. I have to make sure this time is enough for the input to be shown. You get what I'm saying? Should be enough. It's enough for the input to be shown because of the delay, okay? Anyway, that's what I said before. Anyway, good luck and do your best, okay? Thanks.